Matrix form of Maxwell's equations in Fourier space. So we enter this lecture with a bunch of equations of Maxwell's equations in Fourier space, and we want to numerically solve these. So we need to put these into a matrix form and hopefully simplify our notation at the same time. Once we do that, I want to talk about some other things. I want to talk about something called fast Fourier factorization and also some consequences of representing things in Fourier space. So a price we have to pay for this. Matrix form of Maxwell's equations in Fourier space. So this is what we've done up to this point. We've started with Maxwell's equations in real space. We understand that everything is periodic, so we expanded everything into complex Fourier series, expanded along the reciprocal lattice vectors. We substituted in those expansions, and we ended up here with Maxwell's equations in Fourier space. So let's proceed with these. We'll grab the first equation, and we understand that we have to write this for every combination of P, Q, and R. So let's take 3 spatial harmonics along P, 3 along Q, and 3 along R. So 3 times 3 times 3, I believe that's 27. That's 27 equations. And so we write that equation 27 different times. Now, I'm not intending for these equations to necessarily be readable down here. I just want to show that there are 27 equations. And so we can write those equations in matrix form. So, and the matrix form looks like this. And so we will talk about this matrix on the next slide. So let's go ahead and jump right into that. But this looks nice. This is simple and compact. So at top, we see our matrix equation to remind us of that. And then we also have the original analytical equation in Fourier space. And let's go term by term and think about these. First, the terms in blue, these are our unknowns. And almost always we're storing our unknowns in column vectors. And so for here, we're always doing this in terms of column vectors. So let's just take UZ. So that's the Z component of the magnetic field part of our plane wave expansion. And so the U's are the amplitudes of our magnetic fields. This is the Z component. And we have one of these for every combination of PQR. And so we list those serially in a column vector. And I'm using a subscript I here to indicate this could be X, Y, or Z. So up here it would be Z, and over here it would be Y. And likewise, here's the X component of the electric field part of our plane wave expansion, and we can store all of those in a column vector as well. But at first, they're unknown. So really, we want to somehow solve all this to figure out what those are. But they are column vectors. The next thing to look at are those K functions. Here we recognize that they are doing a point-by-point multiplication in Fourier space. That's not a point-by-point multiplication in real space. This is a Fourier space equation. And point-by-point multiplication is done with diagonal matrices. So Ky are the y components of the wave vectors for all of the waves in our expansion, and Kz is the z component of the wave vectors for our waves in the expansion. And so what we'll do, again, subscript I, that could be x, y, or z. Let's say it's y for this one. We will list all of the kx components for each of the plane waves down the diagonal of this matrix, and it's 0 everywhere else. Last, we have this crazy stuff happening to S. Well, if we're storing S in a column vector, there has to be some big square matrix such that if we pre-multiplied this column vector, we would be performing a convolution. That is our convolution matrix. And very often in these Fourier space methods, you'll hear people call these Toeplitz matrices. They are a Toeplitz matrix for one-dimensional analysis, but as soon as we move to 2, 3, or if you're ever doing anything higher, they don't have purely Toeplitz symmetry anymore. But in spirit, they still are sort of a Toeplitz matrix. So expect people to call them that, even though for 2 and 3 dimensions, they're not purely Toeplitz symmetry matrices. So, but that is performing an operation. This ends up being a full matrix, and we tend to have the low order Fourier coefficients running down the diagonal, so the biggest numbers are along the diagonal, and as we move away, we're looking at higher and higher order Fourier coefficients. So we did all this work to our first equation in Fourier space. Very similarly, we could do that for all of these. So each one of these equations is written once for each combination of P, Q, and R. So we end up with 6 matrix equations, and these look very nice. I told you they would simplify down. And that is the matrix form of Maxwell's equations in Fourier space. So our K's are diagonal matrices, our U's and S's are column vectors, there are unknowns, and this is a convolution matrix. This is our permittivity convolution matrix and our permeability convolution matrix. A little bit more about these column vectors. Let's look at one of the column vectors. What do those numbers mean? Well, remember, we're talking about a plane wave expansion, so it's a bunch of waves at different angles. The zero order term is the amplitude, the complex amplitude of our zero order plane wave. Then our plus and minus 1 are the complex amplitudes of the next order plane waves, also called spatial harmonics. S plus and minus 2 are the complex amplitudes of these, and so on. And if we added all of those up, we would actually get a periodic field. It would repeat. And here's the period of that repetition. And so looking at one little repetition, one period of that, we can calculate all of the amplitudes of those plane waves. So that's what those numbers mean. They're the amplitudes of our plane waves. Fast Fourier factorization, or FFF. Let's think about, we have the product of two functions, f times g, and the product equals h. Now, let's say this is all periodic. That means we can expand each of these into a complex Fourier series. So somehow, this multiplication of two Fourier series equals another complex Fourier series. That's all well and good, but it turns out that really only holds when there's an infinite number of terms. And problems arise when we have finite summations. And to solve things on computers, we can't have an infinite number of terms. We need to truncate these. Very often we'll have something like 11 or 21 spatial harmonics along a particular direction. And so we have to pay a price for that. So what is that price? Here we have truncated our Fourier series, and our summations are going from minus m up to positive m. So we have a 2 times m plus 1 total number of terms. As I mentioned, this doesn't have a problem when we have an infinite number of terms, but we will have problems when there's a finite number of terms. And it turns out when there's step discontinuities involved in those original functions, f and g, the left and right side can converge at different rates, and that leads to problems. So let's think about different cases of that. The first case, well, suppose f and g are continuous everywhere. There is no step discontinuity. Well, clearly there's no problem. There's also the case where f or g, one of the two on the left, has a step discontinuity, but not the other. And it turns out that's not an issue either. The left and right-hand side of this equation will converge at equal rates. So no problem as long as only one has a step discontinuity at any one point. Well, now what if they both have a step discontinuity at the same point? So both f and g on the left have a step discontinuity at the same point. It turns out there's actually two cases. Case 1, if f and g have a step discontinuity, but their product happens to be continuous. And this actually happens in electromagnetics. We'll have the permittivity times the electric field, and at a boundary, those are discontinuous, but it turns out the normal component, that product, is continuous across the interface. So this case does happen in electromagnetics. So this is problematic. We will have a convergence issue, but there's something we can do about it. We can fix it. Then the last case, f and g have a step discontinuity at the same point, but this function on the other side is also discontinuous. And it turns out that is not fixable, and our convergent rate will be horrible. If we think we can run a simulation with 11 spatial harmonics, we might need 101 spatial harmonics. And there's even folks out there that argue things never converge. And in my experience, I have yet to see something not converge, but it may take such a ridiculously large number of spatial harmonics that I might just go ahead and simulate things by another technique that doesn't suffer from this. Okay, let's think about case 3 and how we're going to fix this. Case 3 means both f and g have a step discontinuity at the same point, but for whatever reason, their product happens to be continuous. So h is continuous. Let's think about that. So we can kind of jump to our matrix form this way, and let's think about what happens. So let's take f over to the other side of the equation. So now we have g equals 1 over f times h. Well, if f was the one that had a step, if f and g had a step discontinuity, but we bring f over to the other side, it's kind of like we're multiplying 1 times g, so there's only one step discontinuity on the left, no problem. H we've already said is continuous. F has a step discontinuity, so will 1 over f. But here we have a product of two functions where only one has a step discontinuity. Again, there's no problems here. We fixed that by bringing f over to the other side. So let's jump to a matrix form this way. And so we would have fixed our convergence issue. Well, here's something neat we can do. Once we do that, now we can bring this reciprocal back over to multiply g. So we take the reciprocal of f, maybe we'll construct a convolution matrix of it, then take the reciprocal again. So we do this sort of weird double reciprocal thing, and we have fixed our convergence problems. And so this weird double reciprocal thing, which I like to call, that is fast Fourier factorization. And it works really well. So let's think about Maxwell's equations. We have a case where we have the permittivity times the electric field, and at a discontinuity where the epsilon is discontinuous, so will the electric field, or at least the normal component will. So let's remember our boundary conditions. The tangential component of the electric field, that is continuous across the interface. The normal component of the electric field is not continuous across the interface. However, the product of the permittivity times the normal component, this product is continuous across the interface, which of course is going to be a fixable thing here. Okay, so we have, once we Fourier transform and jump to matrix form, we have our convolution matrix operating on this column vector S. Well, our boundary conditions apply differently whether they're parallel or tangential components. So we can decompose our electric fields into parallel and tangential components. And of course, the sum of those two is our overall electric field. Then we can multiply this out, and we end up with our convolution matrix operating on the parallel component or tangential component, and our convolution matrix operating on the perpendicular component. This now gives us an opportunity to mess with these convolution matrices differently. We can do something to the convolution matrix operating on the tangential component and do something to the convolution matrix operating on the perpendicular component. So the tangential component, yes, the permittivity is discontinuous, but remember the tangential component is continuous across the interface. So this is our case 2, and there's no problems. We don't have to do anything about that. The last term, this is case 3. This has a problem, but we can fix this with fast Fourier factorization. At an interface, the permittivity will be discontinuous. So will that normal component or the perpendicular component, but the product is continuous. We can fix that with fast Fourier factorization. So that's exactly what we do. We will take the reciprocal of the permittivity. We will build the convolution matrix from the reciprocal of the permittivity. The reciprocal of the permittivity, by the way, is called the impermittivity. Once we've calculated the convolution matrix of the impermittivity, then we take the inverse of that. So we've done sort of a double reciprocal thing, and it seems like, well, shouldn't that be the same thing as this convolution matrix? And in fact, it's actually slightly different. The numbers are different. Now, how do we tell which components of S are perpendicular and tangential? And it turns out that is a tough problem, especially when we have arbitrary geometries. If we know the geometry ahead of time, we can figure that out. And there's all kinds of different ways that people have done these things using electrostatic simulations or other things. But to make a long story short, I'm not going to get too much into that, but we need another field. We need a normal vector field, and that's what these arrows are showing. The gray areas are showing maybe the device that we're simulating, and these arrows are showing this normal vector field. And notice at the edges of this device, which is really the only place where this matters, we can do anything on the inside or the outside. But right here is where we need to decompose the field into normal and tangential components. So we can see the normal vector field is almost perfect at the edges. And that's what we're looking for. We need this normal vector field. So let's incorporate this normal vector field or normal vector function. So let's remember the fix. We had our convolution matrix operating on S. We decomposed S into the tangential and normal components, and we used our fast Fourier factorization trick to fix a convergence issue that was happening here, but now we have fixed it. So how do we get the parallel and perpendicular components? Well, if we have correctly constructed this normal vector field and then brought it into Fourier space, then the normal vector field times S gives us the normal component of S. If we take S, we subtract the normal component, this must be giving us the parallel component. And of course, we can factor the S out and just see that's the identity matrix minus this normal vector matrix now. That gives us the parallel components. At this point, we can take NS and plug it in for S perpendicular, and we can take identity matrix minus N times S and plug it in for S parallel up here. So that's what we've done. Now we'll take this expression and we will multiply it out. Then we notice each one is multiplying an S. So let's factor out that S. And we end up here. Well, if we compare the left and the right-hand sides, we have something, our convolution matrix, multiplying S. Well, here we have something multiplying S. We have somehow an improved convolution matrix. So that's a convolution matrix that incorporates fast Fourier factorization. Let's think a little bit more about that. So this is the equation from the other side. This is our convolution matrix now that's incorporating fast Fourier factorization. We can express this a slightly different way. We can express this as our ordinary convolution matrix before we even considered fast Fourier factorization and add a correction term, if you will. And algebraically, this expression equals this expression up here if this delta convolution matrix is our sort of double reciprocal convolution matrix minus our standard convolution matrix. And that's neat. So this is our correction to the convolution matrix due to fast Fourier factorization. So this really tends to be the preferred form to write this in. Now let's get on and talk about consequences of Fourier space. So first of all, why are we doing Fourier space? Well, in dielectric structures with low to moderate index contrast, the waves in those structures tend to look rather plane wave-like. So expanding those into a plane wave basis is very efficient. If we were to do this on a real space grid, we might need 40 points per wavelength. Well, in Fourier space, we might only need 5 or 7 spatial harmonics to get essentially the same accuracy. So here's what I'm doing to try to illustrate that. Let's say we have a unit cell that is a triangle. And this top row, I'm representing that triangle in real space. So it's composed of little pixels. Then down here, I'm representing the same thing in Fourier space. And I noticed to get a really accurate triangle, I need maybe 31 by 31 points. With about this same resolution in Fourier space, I need 15 by 15 spatial harmonics. So I'm getting away with fewer terms than I am in real space, and that's the advantage. Now, the higher contrast we go, real high permittivity contrast structures or metals, the efficiency of Fourier space methods begins to bog down. There's all kinds of tricks to help improve that. But at some point, I think the real space methods become the more efficient methods. But there's actually a lot of people out there a lot smarter than me that would argue that and have come up with all kinds of tricks to that. But these do bog down. And so when we use too few harmonics, one artifact is that we're blurring our structure. So here we're representing that triangle, and we can see somewhere, in the 21 to 41 range, it's starting to look like a really good triangle. But you know what? Electromagnetically, if this has a low permittivity or low refractive index, this 5 by 5 or 7 by 7 may behave the same way as this super sharp triangle. Now, that wouldn't be the case if we had a metal here or a really high dielectric constant material. So this is a really good method for low to moderate contrast devices. And we get away, if we're using too few, we're really blurring the device. There's another problem, Gibb's phenomenon. And Gibb's phenomenon, we're talking about these overshoots. So we've taken a square wave, that would be our real space representation. We have expanded that into a complex Fourier series with some number of terms. This M is showing the number of terms in that expansion. And then these lines are showing the reconstruction of that. Notice, no matter how many terms we use, this overshoot stays the same. It gets skinnier. Notice for 101 harmonics, that overshoot's really skinny, but it is still there and it is just as high. And that is called Gibb's phenomenon. And for high contrast structures, this overshoot gets larger. And that's another reason why for high contrast structures, the Fourier space methods really start to bog down. And you can't get rid of Gibb's phenomenon. All you can do is make those overshoots smaller. But when those overshoots are there, that actually is the device that you're simulating. It's just like you have a device where there's a spike in the permittivity right at the edges of the device. So here's what that would look like. Let's say we're simulating a triangle. Well, this would be the permittivity profile. It almost looks like a castle defense or something like that. But it actually thinks there is this shooting up, and actually down here there'd be another shooting down of the permittivity. And this becomes part of your device that you're simulating. If you use enough harmonics, this becomes very, very thin. And so for low to moderate index contrast things, that can become very insignificant and negligible. But for metals, that is still a significant thing to have. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.